In this video, we'll add the final bit of SimPy logic to our model. In particular, we're going to add a nurse consultation to the call center. This means we need to add a new type of resource to represent nurses, and that's going to allow us to have a queue before nurse consultation. We're only going to allow a proportion of calls to be routed to nurse consultation. The remaining calls are going to be routed to the exit from the system. Now, the way we've set this model up is that it starts from empty. So that assumes that the call center will only run for a certain proportion of the day. But what we'll do is we'll modify the logic to allow for a call center that runs 24/7. So if we have a performance measure of waiting time that we want to estimate from this system, that means that the initial part of that time series is biased and unrepresentative of the steady state mean. So we're going to divide up our simulation run length into a warm-up period and a results collection period. A link to the interactive notebook I'm going to use in this tutorial can be found in the description below. And if you've been enjoying the series on simulation, please click the like button and subscribe. That will help out the channel and you'll be notified when new videos become available. Let's start by adding some notebook level variables that represent the default values of the new nurse process we're going to include in the model. The first thing I'll do is add in the number of nurses available and the parameters related to the nurse distributions. We're also going to include the Bernoulli distribution in our model. That's going to allow us to simulate the routing of patients to a nurse consultation and the remaining patients out of the system. So we'll declare a variable here to represent the chance of a callback. So we have two new distributions in the model. We have a uniform distribution that represents the length of a nurse consultation, and we have a Bernoulli distribution where we're sampling if a call is routed to the nurse queue or if they exit the system. So we need to update our sampling settings here so that we have 4 streams of pseudo-random numbers. And finally, we need to add in a default value for our warm-up period. I'm going to set that to 0 to begin with, and that's going to be for a case where the call center only runs at certain times of the day and starts from empty. So we'll add 2 new classes to our model to represent the uniform and Bernoulli distributions. I won't go through these in detail, but in summary, the Bernoulli distribution is a special case of the binomial distribution where there's only a single trial conducted. So we use numpy's binomial method and we set the number of trials to 1. The uniform distribution is self-explanatory. We have a low and a high value and we uniformly sample from within that range. If you'd like to see how I'm building these classes for distributions, I'll put a link at the top now so that you can go back to our random sampling lesson. We need to make 3 sets of changes to our experiment class. We're going to modify the initializer method. So we're going to accept additional parameters for the nurse consultation and the chance of a nurse being required to call a patient back. We'll need to store those parameters and create new distributions that represent the Bernoulli and the uniform distribution. And we'll add in, finally, variables so that we can calculate nurse utilization and mean nurse waiting times. So let's just take a quick look at those modifications. So we've added in some additional optional parameters to the experiment class where we can pass in the number of nurses in the experiment. So in the initializer method, what we're going to do is store those initially as member attributes, and we're going to create a placeholder for the nurse resource, which we're just going to call nurses. So the next change we need to make is to the method of experiment that initializes sampling. We're just going to create 2 instances of distributions here. One is the Bernoulli distribution, the other is the uniform, and we pass in the associated parameters. So we're passing here the chance of a callback by a nurse, and we set the random seed, and we're now creating 4 random seeds. This will use element 2. For the nurse distribution, the consultation, we'll use the uniform distribution. We pass in the parameters, and again, we set the random seed. And again, those set of seeds are controlled by the replication number that we're using. So we get a nice repeatable experiment where we always get the same results for the same replication. And then lastly, we'll modify the initialize result variables method. So here, we now add in 2 lines of code that creates 2 new KPIs that are tracked during the simulation run. The first one is the nurse waiting times. Those waiting times are going to be stored individually within a Python list, just like we did for the call operators. And we'll also track the total nurse call duration, and that will help us calculate nurse utilization at the end of the simulation run. So the main change we need to make is code logic for a nurse consultation. You'll see that this logic is very similar to the logic we coded for call operator service. So I've pre-created a skeleton function here called nurse consultation. And the first thing we'll do is we will record the time that the process began, and we'll call that start nurse wait. And then we'll immediately request a nurse resource. So we've passed in args, which is an instance of experiments, and that contains our nurse resource. So at this point, if queuing has occurred, then the simulation time will have moved on. So we'll just track how long this process waited for a nurse request. And we'll store that result in the nurse waiting times list, which is part of our results collection for the experiment. Remember, we've passed in the experiment as a parameter called args to this function. Now we can move on to the nurse consultation itself. So we'll need to sample from the uniform distribution that's within the experiment and yield a timeout equal to that value. Finally, we'll store the amount of time that call lasted in our results collection variable total nurse call duration that we'll use at the end of the simulation run to calculate nurse utilization. So that's the complete function. A few things to note. The first is that we've indented the code here. What I'm also going to do is add in some debug information. So I'll print out that a nurse has called back a patient and that a nurse consultation is complete. So if we want to run the model in debug mode, we'll see some output. Our next change is to the original call operator service function, where we just need to add in some logic so that a proportion of calls are routed to a nurse consultation. So that modification will occur at the end of this code block. First, notice that the indentation level of this code will be outside of the with context manager for requesting a call operator. So that means that this code will be executed after a call operator has been released. And that makes sense in this particular case where a call is complete and that caller is then waiting for a call back from a nurse practitioner. So the first thing we'll do is we'll sample a true or false value from the Bernoulli distribution. So this will be a Boolean value representing if a patient will be called back or not. We can then use this with some conditional logic to create a nurse consultation process or not. So if we are calling the patient back, we will pass the nurse consultation function along with the process identifier, the SimPy environment and the experiment arguments to the environment process method so that it will then run. If we are not calling back the patient, this will then terminate that process within the model. A new bit of functionality we're going to add to our model is the ability to run a warm-up period. What this will allow us to do is estimate steady state performance when the system is non-terminating, for example, when it's running for more than 24 hours. So the way to implement this logic is with a single event that occurs within the model. So we have a skeleton function here called warm-up complete. That takes 3 mandatory parameters: the duration of the warm-up period, after which this event will fire, the simulation environment, and an instance of experiment. So there's actually 2 lines of code within this function. The first line of code is going to issue a environment timeout equal to the duration of the warm-up period. And the second line of code is going to call the reset or reinitialize results method of the experiment class. So that's it. That's why it was handy to set this up as a method that will set all of our results collection variables to 0 or empty. Just to clean up, I'm also going to add in a debug printout here that if we run the model in debug mode will let us know that the warm-up period has completed. We need to modify our single run function as follows. We're going to make 4 changes. We're going to add in the warm-up parameter, which I've done already. We've called that WU_period. That's going to default to our warm-up period, which in this case will be 0. We're going to create the nurse's resource and add that to the experiment. We're going to schedule the warm-up complete process. And then after the simulation is complete, we also need to then calculate the mean waiting time and mean utilization of the nurses. So let's modify that function. So the first thing I'm going to do is create the nurses. Then what I'll do is I'll add in the warm-up period. Remember, that is just simply an event that is scheduled to complete after the warm-up period. And we will need to now run the simulation model for the combined length of the warm-up period and the results collection period. And then lastly, I've pre-done this because it's the same as before. We are going to calculate the mean nurse waiting time using our experimental results. And we're also then going to compute our total nurse utilization during that replication of the model. So we're going to make 2 small changes to our multiple replications function. The first is that we're going to pass the warm-up period as a parameter to the function. That's going to allow us to vary that, turn it off, turn it on, and change the length of that warm-up period. That parameter is going to be passed as an optional parameter to single run. So we'll now run the model for the length of the warm-up period plus the results collection period and discard all of the statistical results within that warm-up period. Results are returned to the function as normal, and then we convert those to a data frame where the rows contain the replication number and the column contains the performance measures for that replication. So let's have a go with that revised setup. We'll create a default experiment to begin with, and we'll pass that to the multiple replications function, which will run 5 replications of the model. So we've got here the performance measures, and then we've got some summary statistics for those. So if we look at nurse waiting time, we can see that on average, callers were waiting for about 27 minutes for a nurse, and the utilization of nurses was about 97%. Let's vary some of the parameters for nurses. So we'll change the number of nurses on duty to 15. What else is available? We'll also vary the parameters of the uniform distribution for nurse consultation. So we'll change the upper bound of that in particular. So we'll set that to 30 and rerun. And we can see that the system copes with that. In fact, mean waiting time for nurses is a fair bit lower, and that's because the nurses are not quite as busy as before. If we wanted to model a system that was running for over 24 hours and we were interested in the steady state means, we could include a warm-up period in this version of the model. So if we set that to 50 minutes to start up with and run the model, we can see that both the mean waiting time and the utilization of the nurses has increased, and that's because we've discarded that initial transient within the output that was biasing the mean estimate away from the steady state, effectively a large number of zeros within that initial period. So we're now finally at a point where we can create an interface for our simulation model using Streamlit, and that's what's coming up in the next video. In the meantime, you might be wondering how I created that experiment class. If so, you can check out this video on screen now.